Now, on the S4 sponsor stage is the session from PAS. Please welcome Mark Carrigan to the S4 sponsor stage.
Curtsy or bow, I'm not sure. Anyways, thank you all very much for coming. Going to talk a little bit today about sort of the differences in forensic analysis and response in the OT world versus the IT world, and go through some specific case examples. Okay, so let me first talk a little bit about what a control system does. And there's an analogy I paint that I think kind of makes sense. If you think what a whole ICS or OT is, it's essentially the brain and the nervous system of an industrial process that runs the plant. The controllers has all the logic and how we do everything. The wires go out to the field like the nervous system that make a valve go up and down or do different things. And when we're dealing with forensic analysis, I want to think more beyond just security forensic analysis. And whether it be an angry insider getting access to a system and causing problems, whether it be an external threat actor, or the person who has done by far the most damage to industrial processes is a well-intentioned insider making a mistake, I must have good information about those OT systems to have an effective forensic response system to deal with scenarios where I have a concern and I have to restore back to where I need to be. So let's talk a little bit about what is forensic analysis. It's a well-understood field. I'm not going to go into all the detail about the science of forensic analysis, but it entails a number of things, starting with identification and preparation, knowing what the data sources are, prioritizing, preservation, and collection of the data that I need, and you have to be doing that before the event, not after the event. And once I have that, that sets the stage for actually doing an analysis after an attack or some kind of event, examination, analysis, reporting, and reviewing the results. The second thing is that forensic analysis and response is very well defined in the IT world. And the IT world being our computers and all the business networks and everything else. And there's lots of companies that do this, a lot of data is being collected, things are going to the SIMs, Windows event logs, network traffic, lots of data preservation companies are collecting so that if there is an event, they can recreate it and reverse it and do all the things they need to do. But the field is less well defined and less mature in the OT side of the business, and the OT being the controllers, smart instrumentation, advanced process control, all these things that actually impact our physical processes. And the data that you need in these first three areas, the identification, data sources, and the data collection, is very different. I need a different set of data if I'm going to respond to an incident. I need different information about the assets and event logs and everything else that traditional IT work practices and tools very likely are not capturing as a part of a forensic situation. So, it's 12 a.m. and a system that controls a safety critical process that's really important to my business isn't working right. It's acting squirrely and weird things are going on. And the operators are on the phone. I don't know what's taking place. And you don't know, is this a technical problem? Or there might be do we get hacked? What's going on here? So who are you going to call? Who is the people you call? And I submit, when it's time to go to respond to something like this, it has to be a cross-functional team. You need people that understand security, you need people that understand the process, and you better have a control engineer that knows that darn system if you're going to respond to this and effectively deal with the situation. So I'm going to walk you through, this is a real case scenario. I know of this because a person that works at PAS was responsible for security at an oil and gas company, and this happened to them. An interesting response how they dealt with it. This was actually at 2 o'clock in the morning, and all of a sudden their IT group got notification through their IT security that a device down in the OT network was attempting to make a connection with a known bad URL address off in the internet. Whoa, not cool. The first thing the IT team tried to do, and they made a few phone calls, is, I'm going to kill that device. I'm going to shut it down. It's down in the OT world, but I can get to it. I'm going to kill it. When they made the call to the plant, the only thing they knew was the IP address. It's this a box. So the controls engineer said, what is it? Which is it? They said, I don't know, but I'm going to kill it. They said, you better not even think about killing it. Because if that is a box associated with process control, in this case a refinery, in my critical unit, fluid cracker, whatever, you guys could cause an explosion. You are not touching that box until we figure out what it is and what's going on. So what do? They got in the car, they had to drive out there, they got the control engineer, everyone, and they tried to figure out what this darn thing is and what it is and what we're going to do about it. My point is, of this one incident and everything else, is the typical IT playbook needs to get modified when we talk about OT. And why is that? Well, the main reason is there are some critical differences in the missions between IT and OT that's not going to go away. There's lots of talk about convergence, and there's a lot of improvements in work practices, but there's key differences that exist between these two worlds that, like I said, are not going away, and you better consider as part of your forensics response plan. Let's start with IT. Generally speaking, the boxes on our IT network have flexible applications. I have a server that has lots of different things on it, people doing it, and lots of different people do different things with that box purposely. Think about your own laptop. I have it doing all kinds of stuff in different purposes. The second thing in the IT world is that security trumps availability. If I have a critical thing that needs to be patched, if I'm worried about a security or something talking to a bad URL, I don't care. I'll kill it. I'll shut it down because security is more important than having the device available. The next thing in IT is things are relatively new. The life cycle of devices in the IT world, 3 to 5 years. It changes depending upon things. But generally speaking, we have relatively new things that are out there, so it's easier to take advantage of security in the IT world. And finally, it's relatively homogeneous. When you're responding to a cyber incident, if I really understand the Windows environment and IT and network traffic, I can respond to that incident. It's relatively the same. Let's flip it over to the OT world and control systems. First big difference. They are designed for a specific purpose. You don't take a server associated with a DCS and load Excel on it so you can build a financial spreadsheet. No. It has a job, let it do its job. The second thing, and this is the biggest difference, availability trumps security. Don't believe me? Go take a look at a typical refinery or chemical plant. You'll find devices with Windows 2007 on it. Because if they upgrade it, they could break stuff. They have to be very careful. So you have to let availability trump security, live with security concerns, and only upgrade them and do things when you can do it in such a way you don't affect the availability of the control system. Because there's a good chance that control system, again, is controlling, it may be dealing with a safety critical process. This stuff is old. Most of it grew out over time, especially in the large processing industries where they built the plant 30 years ago. They put in systems over time. Distributed control systems typically have a life of 20 years. PLCs typically have a life of 5 to 10 years, depending upon the application, sometimes even longer. Safety systems as well. You don't upgrade those things because they are reliable, and it's really expensive. I can swap out a server, ghost the thing, restore it, we're off and running. You can't do that in the OT world. You can't just ghost it and restore it. It's much more difficult. So it stays to be old. Finally, it's heterogeneous. Very different. A DCS from one vendor is not at all like a DCS from another vendor. A PLC, etc. They look different. The configurations are different. The programmings are different. They're all hooked together talking to each other through protocols. So if I'm going to respond to something, I need a lot of different domain expertise. I need to augment my IT expertise with OT expertise to understand that environment. So I point this out because if you don't keep this in mind when designing your forensic response plan, you're going to have holes. And you've got to deal with this environment. And again, we're not going to just make these differences go away. They're going to be here for a very long time. So, what is it? How do we really help during those first 3 things that we talked about as far as preparing for forensic response, having the data? Well, first, you need an inventory of everything you got. I need, even down to level 0, the sensors in inventory, because some of those things are smart. They're programmable. So they can actually operate independently, part of the process, depending upon the nature of it. I need all the information about all the controllers, the PLCs, which are basically special computers that run in that environment. What is their configuration, all the programming therein? That's what detailed configuration is. All of the information, and I mean extremely detailed. Here's all of my tags and the properties of those tags, and it's a flow controller with this gain setting that talks to this totalizer, whatever. You got to have all of that. You got to be able to baseline what that configuration is and then know what all the changes are. We're going to go through that here in a minute so that you can, if you have to go back and recreate this, understand the changes that may have happened over time. Because ultimately, if my goal is to cause physical harm, I'm probably going to make a change to the configuration to make the control system do something it was designed to prevent. And finally, you got to have all the documentation required to do all of this. Again, this is Forensics 101, and nothing here is not all part of the good forensics plan, but again, it's just different in the OT world. And the practices, the technology, and the expertise is just different. So, I'm going to give you a very specific example. If you were at my talk this morning on stage 2, I went through various weaknesses that are really easy to exploit to cause harm in industrial control systems. This is one of those examples, so if you're here this morning, I'm going to repeat it. I apologize, but for those who weren't there, I can explain it. In most control systems that you get, there's things called functions, okay? A control function, like a flow controller function. It's like a piece of compiled code that you grab off the shelf and you configure it with your information about your process. Like here's the ranges of the process we're in, the engineering units, like am I looking at gallons per hour or gallons per minute, alarm information, all of these things that you configure to make that control function work. In this case, a flow controller. One of those parameters that you set is a thing called output characteristic. I won't give you the specific parameter name. It varies from different systems, but just think of it this way. I have a set point, and let's say I want the flow to be 100, and so the operator says, make the flow 100, and the current value is 90. Well, your control function will solve the problem and say, oh, there's an error here, and there's a difference between where it's supposed to be and where it currently is. As a result of that, I'm going to tell the valve to open up more and keep opening up and eventually get the process to where I want this thing to be. That's what the control function does. It solves problems, it tells an output to do something, it reads it again and solves it over and over and over again. That's what it basically does. This thing called output characteristic has two settings. It's binary, it's one or the other. Direct or indirect. And basically, direct is, if I have an error, it's a positive thing, open the valve up more, essentially. If I flip that setting, so I change that setting, very easy thing to do, really easy to do, then with that error, it's actually going to start to close the valve more and more and more, just by changing that one setting. In many systems, I could change a lot of those things really easily. It's a simple thing to do. And in fact, it's hard to read on this right here, but you'll be able to get a copy of the slides. This is a very simple line of code that does this across multiple systems. I'm going to go to the next slide to kind of explain what this is. Inside the system, I have an application that does things. It reads information from different control functions to do something complicated in control, whatever it happens to be. And so this is Rev 1 of that particular program. What I have done here is I have injected code, and again, you can see it when you get a copy of it if you want to see what it does, but let me explain what this thing does. This says at midnight, I'm going to go out to a selected set of devices that are out there. I'm going to reverse that output characteristic. 15 minutes later, put it back. Let me tell you what's going to happen in that particular case. Every night at midnight, this system's going to go crazy. There's going to be all kinds of weird, squirrely problems with the controls. In fact, if I do this on a slow-acting process, it won't shut it down, but it'll act weird and squirrely. And then 15 minutes later, it's going to restore itself again. The first time that happens, the operator's going to go, what just happened? And he'll write it off, he'll write it down in the book and everything else. But then you're going to be chasing your tail on this particular thing. The way that I have done this in this particular system, there will be no record of this. There'll be nothing out there that says this is happening at midnight every single night. This happens in the background by using the native programming language inside that particular system. The only way you're going to find this is essentially finding this code injection on the before version and the after version of this program. I could do many, many more different things, all kinds of crazy things. Control engineers look at this kind of thing and laugh and chuckle and say, oh man, you want to get nasty? I could do all kinds of stuff with this type of thing. My point is, though, is that you've got to be able to get this detailed configuration, not just things going over the network, not just Windows event logs and the things that are typically there in the IT forensic world, but this level of detail about all the configuration, and there's lots of it at a typical facility and across an enterprise, and be able to detect these types of injections and changes that can be a problem. One last thing I will point out is that these types of things I talk about, whether changing an output characteristic or other things, the reality is, I talked earlier about this is valuable not only for security, but it's also valuable from a operational perspective. A well-intentioned person has caused much more damage than, quote, an attacker ever has. Okay? Mistakes happen. You don't realize what happens. You don't realize that changing this here affects that thing over there, and it causes issues. And so there is an added benefit of improving your forensic response for security reasons, is that if you have this information, you can actually help to avoid and recover faster from just someone did an oops. And far more industrial accidents and loss have taken place from the oopses than from a deliberate attack. So getting into, okay, that's great. What are we going to do about it? Yes, PAS does offer technology to help you do this, especially around the configuration of these very complex, old, and heterogeneous OT devices. A little bit about us. We actually started in 1993 not as a security company, but as a process control company. We developed software to help people better manage the configuration of all the things that sit in their plant, understand what the configuration is today, what it is tomorrow, document all the changes to help them just better manage those systems. And people have been buying our technology for over 20 years under the guise of and under the benefits of improved safety and reliability. But that exact same data can also be tasked and reused as part of a IT security, or basically a cybersecurity strategy as part of forensic response. If that thing goes off at 2 o'clock in the morning and I have those IP addresses, I want to see what that box is, I want to understand what it's controlling, and I want to see if any changes have been made to the configuration that could impact the control of that process. And we do have that data, and we do allow that to be shared with across the organization, so you can have a true integrated forensic response team that's going to deal with OT. I need that person that understands network traffic and Windows event logs and the path of ingress, if you will, that a traditional IT person knows. And they better be part of the team. But similarly, when it's this box and I think it's a problem, and it is a DCS controlling a separator on an offshore production platform. You better have that control engineer that knows that system and knows that process, because he's going to be critical to understanding what the potential impact is of any changes that were made. Okay? So that is it for my presentation. Does anyone have any questions? That language I gave right there? Does anyone know? That gentleman knows because he has written it. This is actually called AMCL. And this is a programming language that's specific to a Honeywell DCS system. It's native inside the DCS, and it is pretty darn similar to Fortran in its construct. But it's not quite Fortran, but they basically took Fortran, made it a derivative, and made it available in the system. And this is all, there is so much AMCL out there controlling critical processes, you cannot believe it. I'm sorry? This particular code, it actually runs on a Honeywell box. It would not run in Windows. It would only run on a specific Honeywell box. There's different types of boxes. There's basically Experian and app nodes. This is all Honeywell language. They are not Windows boxes. They are Honeywell boxes. This would do nothing on the Windows side. This is running on the actual devices that sit in a distributed control system in this case. Now, this does apply to other systems, like in Fox IA, there's a thing called HLBL, which is kind of like a somewhat equivalent in there. In Emerson Delta V, SFC, sequential function chart. Every system comes packaged with basically a custom coding thing that's unique to their system. Some look like Fortran, some don't. Just depends upon the system. At that type of level, and it even goes beyond that. In this particular case, yes, I'm going to tell you, this is Rev 1 of the document, this is Rev 2. I will tell you first that it changed. AMCL has, it's a compiled thing in there. So if someone adds a new program, I'll tell you. If someone deletes a program, I'll tell you. If someone modifies it, they'll tell you. And I will do the compare to show you what that is. But we actually go beyond that. There's a lot of things that aren't programs, they're settings. So I remember that flow controller I talked about? A typical flow controller might have 30 things you configure to make it work. The engineering units, the alarms, the P&ID settings, like a gain setting for a flow controller, all of those things. And I will tell you every one of those parameters and how they change over time.
You can do this across most of the major industrial controllers, such as the Allen Bradley, the Siemens, Mitsubishi.
Those are all part of my library, yes. Now, every single possible control system out there, we build the library as we go, but we have a ton of them because we've been doing this for a long time. We've been at this, again, for reliability purposes since '93, and so we built out a very large library. But yes, Honeywell, Siemens, Yokogawa, depending upon the flavors. I should point out that 2 Honeywell boxes look so different. It's amazing on older versus newer generations. Same with Siemens and ABB and everything else. So we do have different, what we call basically digital twins of the configuration of all these different systems. One last shameless plug. Yes, we're at the Cabana. You want to see some of this, I'd welcome you to come by, and you can actually see this stuff, and I'll show it to you. So again, it sort of depends. When you start getting to source code and backup, the data that we get typically can be used for that, but there's some system dependencies there about what data you have to get. It gets really, especially in DCS world, all the stuff you need that is, quote, the backup is system dependent. So I'd have to go into the specific system about what we've got. For the most part, yes, but I want to be safer, not ubiquitous, because, again, if someone tells you I got a universal backup solution for the OT world, run and hide. It is complicated, so it takes a little bit extra work. Yeah, good question. Good question. So at the end of the day, again, I will get to the answer, but let me put it this way. At the end of the day, what we're talking about is the brains of your process, which is the configuration of a control system, all the tags, the programs, and everything else. And whether it's done by an angry insider, external threat actor, or accidental misconfiguration, it doesn't know. It just did what it was told to do and then caused a problem. Okay? So if you will, the discipline is the same. If I'm responding to this thing isn't working right, whether I know it's because of a production problem and I have to go find out what changed and what the story is, or I suspect that someone has gotten in and doing stuff, the data you have to analyze is exactly the same. So it doesn't matter at that point. But in regards to, quote, what is fail-safe? This is another thing I can tell you with certainty. No one can provide a technology that can not only capture all the change, but tell you that every change is good and righteous. There's so many things that you can change in so many different ways. And to be sure, okay, someone changed the gain setting on that flow controller from 0.2 to 0.25. Is it good or not? Someone's got to look at it and make that determination. And that's really some eyeballs that are on there. So to really deal with this, you really have to implement good configuration management policies on the devices, get the data, examine it from time to time, have good configuration baselines, and then have the ability to restore back to a point in time prior to the concern, whether it be hours or a week or whatever. You got to be able to do that. Okay. So again, it's sort of like the attribution. Again, in this one example I gave later, at first they had no idea what the source was. Right? They didn't know the cause. Is this a hack or is this something else going on here? So when you first start off, get into is it a mistake? Is it malicious? The forensic analysis will bear that out. So I hope I answered your question. I got you. So for those who couldn't hear it, basically and I'll summarize it, is basically how can I not just think in terms of forensics, but bring in the concept of resiliency into OT to improve essentially their stand-up and capability, right? There's a lot of things that we have to do. You know, there's things that we want to do, multi-factor authentication. We want to control who has access. There's a lot of things that we do. But a part of this is doing good configuration management, knowing all the configuration of the devices, monitoring for change. That does cost, technology can help, but it does require a work process. And we don't have to do it for everything. If it's an air conditioner in the building, that's not big of a deal. But if it's a critical process, you bring additional configuration management to my most critical devices and manage those devices to improve resiliency. That's what you really have to do, okay? You bet. Any other questions? Yes, sir. Nothing gets deployed on the device. Every single one of these systems has a mechanism to, I'll call it puke out or regurgitate its configuration, all right? And it's unique for every system. So what's your driver to get the data? Well, tell me the system, and I'll tell you the mechanism that we do so. And so it comes with the device ships with software. So in Allen Bradley, there's a thing called RS Logix, which is the programmer that you load in there. So that can get the configuration file from the PLC. DCSs have different mechanisms to produce its configuration. And so basically what we do is we ask the system of its engineering tools to say, please provide your configuration backup and put it here. Now, the results of that can be files, it can be databases, it can be combination. Some of these things are actually binary files. Sometimes they are text files. Sometimes they're SQL databases. It just depends. So once it has spit out its configuration, that's where I take it from there and then bring it off into my application to do what I do. That's a very good analogy. It's a centralized configuration management for all the different things. But other things we do in there too, like we tell you interconnections. Wait a minute, that register in that PLC through Modbus goes into that tag inside the DCS system that goes up into that tag up in Pi. So we also basically do all the cross-referencing and map the dependencies between the devices, not just inside of the devices. At the end of the day, it's an automation network, not an automation device. Man, you are like just doing my pitch right now. This is awesome. So yes, part of that as well is, hey, wait a minute here. These two things are talking together, but this says it's gallons per hour. This says gallons per minute. That's not right. So that type of validation, because we know the properties that have to line up, that have different names and different devices. So we kind of normalize this and do that type of data validation. So the question is, hey, did you guys do a study about these kind of configuration errors? And we did do a study for one company about looking for these types of errors actually that existed between the control system and their Pi historian. Things like the engineering units are different, or the ranges are different, or things like that. And we found almost 8% error between these two systems that can lead to bad data for decision making. So there's a lot of operational benefit from managing this stuff as well.